So we're now going to start discussing continuous random variables, which are different from what we saw last week, simply because last week we were talking about discrete random variables. And so it's helpful at this point to consider the difference between the two variable types, discrete and continuous. I think it was module 2 when we talked about this. We talked about discrete data and continuous data, both of which are quantitative. Does anyone remember the distinction between those two things? What is the difference between discrete quantitative data and continuous quantitative data?
Discrete deals with integers that you can count, and continuous is kind of the range in between all the numbers, the fraction, the smaller parts in between.
Good. So integers are a perfect example. If I'm counting how many times something happens, 1.5 isn't really an option. 1 2/3 is not an option. It's 0, 1, 2, 3, etc. Those are perfect examples. It doesn't have to be a counting number, though. The key thing with discrete is that we jump from one value to the next. There are two values between which we know nothing can happen. Right? And so counting numbers are an example of that, but there are other numbers as well. If I'm talking about how much money I'm charged at a cash register, that's technically a discrete value because they're not going to charge me 1.5 cents. They might charge me 1 cent, 37 cents, 23 cents, but there's not going to be a fraction of a cent that I actually pay them at the cash register. So that's discrete data. And continuous, on the other hand, can take on any value in a range. So some simple examples of the difference between those things. Continuous data might be things like temperature or speed. Right? The temperature can be anywhere in a range, and how accurate my measurement of the temperature is might actually just be due more to my my measurement instrument than anything else. If I want 3 decimal places, I can get that. If I want 4 decimal places, I can get that. And any value in that range is potentially possible. That's continuous data. Discrete, on the other hand, again, I'm counting things, or I'm measuring something where it has to fall at this value, or at the next value, or at the next value. There is a natural next value in each case, and that's what makes it discrete. All right. So the reason why we're talking about that now is the distributions we saw last week, including the binomial distribution and the Poisson distribution. Those are discrete distributions. And we also saw cases where you could describe a discrete distribution by a table, right? Those are all discrete distributions that allow us to model situations relating to discrete data or discrete variables. Just as you might expect, then, there are continuous distributions that represent the types of things that can happen with continuous variables and with continuous data. Okay. That's what we're going to talk about now. So it's more complicated in the sense that I can't simply list out the values and list out their probabilities. It becomes a lot harder to think about the probability of a single value. Okay. So that's actually the next natural question. When I do a discrete distribution, probably the easiest way to do it is like we did in that example at the start of the class. I can list out the different outcomes because they're discrete, so I know I can list them. And I can list out their probabilities, and then I can add those numbers to get a total probability of 1. Right? I know that that always will work, and that makes my life much simpler when I'm calculating expected value and things of that nature. So if I want to find the probability of a single value, the probability that x equals 2, for instance, or the probability that x equals 5, I can always look in the table or use whatever formula I know I have to compute that probability. Okay? And we did that with Wagnar's calculator in a few cases. We calculated the probability that for a Poisson distribution we saw a single specific value. And we did the same thing last week for the probability that we see a single specific value in a binomial distribution. And I can look at the example with the lottery that we looked at before. The probability of winning the grand prize was 1 out of 700. That's a single value, and I know the probability of that single value, and it's non-zero. Well, the thing with continuous distributions is because every value in a range is possible, the probability of a single value, you're asking for the probability of 1 point in an infinite collection of points. That is always going to be 0 if it's a continuous distribution. So we have to change the way we look at the question of probability for continuous distributions. We can't really ask for the probability of a single value. But what we can do is we can ask for the probability that the value we look for falls in a certain fraction of that entire interval, right? So if I'm measuring, let's say, speed, and I'm just going to declare that speed has to be between 0 and 120 miles per hour, the chance of me measuring a speed of exactly 63.1257 miles per hour is 0. But the chance that I measure a speed between 55 and 65 is something I can measure. And that's what we'll be doing with continuous distributions. We'll be measuring the probability that it falls in a range of values. Okay? Now that range might be between two numbers. It might be anything less than a certain number or anything greater than a certain number. Those are all different ranges or intervals, as we call them in mathematics. And that's what we can do. We can find the probability of those. Now how do we do that? This is where continuous distributions are very different from discrete distributions. When we looked at Bogner's calculators for the discrete distributions, we saw the essentially histograms, what it looked like, that listed out the probability of each individual value. And we could kind of scroll through those individual values and find those probabilities. It also made it easy to calculate the probability that we get a number less than or equal to 3, because we can add in the probability of 0, probability of 1, probability of 2, and probability of 3. Right? Those 4 bars together give us the probability that x is at most 3. That doesn't work for continuous distributions because there's an infinite number of values in that range. So how do we handle it? Well, what we do is we actually use area to compute probability. So what we do, each continuous distribution has what's called a probability density function. Okay? And that describes, in a sense, the density of the probability at each place. Underneath that curve that we draw, that probability density function, the area between it and the horizontal x-axis represents probability. So if I find between two values, what I do is I draw in my probability density curve, I mark off those two values, and I shade the area between them. However much area that represents, that is my probability. And they are set so that those probability density functions have a total area underneath them that's equivalent to 1. And as you might expect, the area under a single point is 0. So everything is consistent with what I would expect, but calculating it is not quite as simple as what we saw before. So again, Bogner's calculators will make our lives a lot simpler. There are equivalent calculators on other sites that you're welcome to use, but I would generally recommend using Bogner's if you're going to use a computer calculator. If you have a handheld TI-83, TI-84, those will do them as well, and those are also pretty nice, pretty easy to use. All right, so a probability density function gives us a way to compute an area that will represent the probability of a specific interval. When the interval we're looking at is every number below a fixed bound, we will use what's called a cumulative distribution function. And that represents essentially the probability that a randomly selected value will be at or below that given point, whatever it happens to be. Okay? Now this is the same as the area under the PDF that is to the left of that point. We'll draw some pictures and you'll see what I mean by this in just a moment. But for continuous distributions, we have a PDF, which is the curve under which we can calculate area. And we also have a CDF, which is a function that tells us the area to the left. Okay? So it's the area under that PDF to the left of whatever input value we use in the CDF. All right. So I do want to show you a couple of examples of continuous distributions that we will not be using. I'll show you Bogner's calculators for those as well. We won't see them again after this discussion, but they will help give you context for what happens with the normal distribution so that you see what's different about that distribution itself versus what's different about continuous distributions as a whole. So are we ready for the next 1, looks like we are. Okay, so one example is the uniform distribution. And for a uniform distribution with two parameters a and b, what we're looking at is an interval from a as the left endpoint and b as the right endpoint. This is the continuous analog to the equally likely events, like rolling a six-sided dice. If it's a fair dice, each number of pips showing has an equally likely chance. It'd be 1/6 probability in each case. That's the discrete example. A continuous example is the uniform distribution. So the UAB would be the interval from A to B, where every possibility is equally likely. Turns out there's lots of ways to calculate this. I'm not going to bother you with the calculations for now. But if I have a uniform distribution, the mean is always the average number in that interval. Kind of makes sense. The mean would be the number right in the middle if everything's equally likely. And that's what this is. It's A plus B over 2. The standard deviation is more complicated. But long story short, it's always going to be B minus A over the square root of 12. Don't ask me why. I could explain it, but it would take more time than we have for the rest of the day. So let's not do that. Here's an example with specific parameters. So the interval from 0 to 20. I drew in the PDF. Now technically, it's on the x-axis to the right of 20 and to the left of 0. I didn't draw those in because that does not influence my calculations of probability at all. So I will often ignore those extra sides. But in the middle region where we actually care about it, between 0 and 20, the height of that probability density function is 1/20th, and it's flat. It's equal everywhere. Now, if it's a uniform density, I could ask the question, what is the probability I see a number like between 0 and 10? Okay, well, if the range of possible values is between 0 and 20, and they're all equally likely, then the chances of seeing something between 0 and 10 should probably be 50%. Right? 10 of the 20 underneath it would be about 50%. The cumulative distribution function, well, it's 0 until you hit that first possible value, so it's 0 to the left here. Once you hit that first possible value, we start to see a positive probability. And for every value in that region, it's whatever the value is out of 20. It's the fraction of the interval that we've seen so far. Once you pass 20, then you've seen everything that happens. So the area to the left includes everything that's possible, and so thereafter the cumulative distribution function has to be 1. Now I drew in an example. If I want to find the probability that I see a number between 0 and 15 under this particular distribution, well, 15 out of 20 is 3/4, so that should be 3/4 as a probability. Okay? And using this cumulative distribution function, if I plugged in x equals 15, that's what it would be. And you can see this picture represents how I compute that area and use it to find a probability. Okay? The area of the shaded rectangle here is 0.75. The unshaded area right here is 0.25 because the total area has to be 1. Easy way to see that, the height is 1/20th and the width is 20. 1/20th times 20 is 1. Alright, so uniform distribution is a pretty simple one, at least geometrically, but it has some interesting properties that you might not have predicted. This one's not too bad, but this one's pretty interesting. From that, we can find probabilities all throughout that range. Now, Bogner doesn't have a calculator for this because, again, it's pretty easy to just take the number and divide it by the total range. He does, however, have an example for the exponential distribution, which is another type of continuous distribution. So this distribution has a single parameter called lambda. And if I have a random variable that's distributed like an exponential with parameter lambda, then the mean is 1 over lambda. And the standard deviation is also 1 over lambda. Okay? So this is kind of similar to what happens with the Poisson distribution, but it's a continuous one instead. And there is a formula for calculating it. It turns out that the formula there, in fact, I think I have it here. I'll show you that in just a moment. This is what the PDF looks like. It looks similar for any value of lambda. I just drew in the one for 5, just to give you an example. And for that particular one, the average would be 1/5, or 0.2. And the standard deviation would also be that. Might shift over for a moment. No, I'll do the rest of this slide, then I'll show you on Wagner's calculators what that looks like. So the probability density function has the form lambda times e to the minus lambda x. If you've seen this e before, great. You probably have it in algebra class before. If nothing else, you've probably done continuously compounded interest. A equals p e to the RT. It's the same e. It's called the natural exponential number. If you've taken a class with me before, I mentioned it comes up in a lot of places. This is one of those places. Its cumulative distribution function is 0 until you hit the first possible value, which is at least 0. And then after that, it has this exponential form, 1 minus e to the minus lambda x. Okay. And so one interesting feature of that is it gets more and more area as you go, right? So you're collecting more and more probability. It never stops. There is no upper limit on an exponential distribution. It can be as high as possible. Obviously, the higher values are less likely because this graph is going down. The total area under that curve is 1. Now, if I wanted to find the probability that my x value was less than 0.2, in the case where I have that same lambda equals 5, I have a 63.2% chance of finding a value below the mean. This is also a good place to mention, how would this change if I said less than or equal to 0.2? Think about what that means. The difference between the probability of x less than 0.2 and x less than or equal to 0.2, the only difference is that 1 point at 0.2. And what's the probability of that single point?
0.
0, right? It's a continuous distribution. It can be anywhere. In fact, in this case, anywhere on the right side of the x-axis. It can be anywhere in that range. So the probability of a single point is 1 over infinity, and that's 0. Okay. So that's what continuous distributions look like. That's just 2 examples. Again, let's switch over quickly to Wagner's calculator again. We look at Wagner's calculators. There's a number of continuous distributions here. Right now, we are going to be looking at the normal distribution in a moment. We just saw the exponential distribution. I'll just show you that in a second. Later in the course, we will definitely talk about chi-squared. I don't think we'll have a chance to look at f, but f is also, I think it's considered in your book. It's related actually to the linear regression stuff that we will see. We will see the t distribution. That's the one I mentioned that's coming up in later modules as well. So you'll see a lot of these. Click on an exponential distribution. I only need a single parameter, so that parameter 5. There it is. My mean is 1 over lambda, so 1/5. That's what 0.2 is. And my standard deviation is also 1/5, 0.2. I wanted to find the probability that it's less than 0.2. And there it is, 63.2%. And that represents the area underneath this curve. Okay. Now, in this case, there was a formula for doing that, but for many distributions, there isn't a direct formula. And what I mean by that is there's not a formula you can plug an x value into. If you've taken calculus, you may recognize the idea of area under a curve as one of the key ideas in calculus. In calculus, there are three main things you learn about. You learn about limits, you learn about derivatives, which are built by limits, and then you learn about integrals, which are essentially the reverse process of derivatives, can also be built by limits, and integrals represent area under a curve. So if you compute an integral, you can actually find the area under the curve, and sometimes you can do that symbolically. In that case, you can produce a formula, and that's what happened with the exponential distribution. So we have a formula for finding the area to the left of a single value. With the normal distribution, we don't have a formula. We, of course, can write it as an integral, but that integral can't be evaluated symbolically. It has to be approximated. And so for that case, you'll have to use either a calculator or a table of values. And I will show you how both work. But in this class, I will focus on using a calculator. It's great if you know how to use the table of values. If you've done it before, or if you want to do an example or two in the class, that would be great. It will help you with understanding what's happening around the normal curve. But it is not only more difficult to do it using the table, it is also less accurate, because the table has to have you round the z-score that you use. Whereas with a calculator, we can use as many
Clara, there's other
as we
food
have
in here,
available to
the
us.
house. You're just being
So
a
the calculator
butthead.
will
You
be
have
more
burgers,
accurate,
you have
it
pizza,
will be
you have...
faster, and as long as you understand what's happening behind the scenes, it's perfectly fine to let the calculator do the legwork.
No.
Alright, questions about that?
Your chicken tenders in here.
She's attacking me.
Yep, she wants to
Perhaps it would be best to just march right along.
Clara, you're really feeding
I do want to
her.
emphasize, I showed you these two distributions simply so you could see some other examples
Not the cookie.
of a continuous distribution.
I know that's not.
What we'll be working with primarily are the normal distribution and then later the t-distribution, but it's related to the normal distribution.
Does Bella want a cracker?
So our third and most important example of a continuous distribution is called the normal distribution. And that's kind of a loaded term when you think about what that means. Like, where did the term normal come from when we describe this? We'll see why in a little bit, but for now, just take my word for it, that's the name. The normal distribution is applied to a variable distribution that looks like it will be unimodal and symmetric. Now, have we seen that before, that description before in this class?
What?
There's another term we often use for that.
With all the stuff I don't want. Like my old clothes that don't fit me, my old toys that I don't
Anyone remember?
But I'm definitely not giving away that.
The bell-shaped curve?
Yeah, when we talk about a bell-shaped curve, one of the key features of that is the center is right in the middle.
I just got that. I'm a big
The center is the biggest part, and it's symmetric on either side, right? That's what makes that bell shape. Well, the normal curve represents the PDF of a normal distribution, and it is a bell curve. So this is really what we have in mind when we think about a bell curve. And obviously real-world data may or may not be precisely normal, but it may be pretty close to it. And if we have enough symmetry, we can use a normal model to approximate it. Okay? We'll see later that there are situations where a normal model is appropriate for modeling sampling information. So how do we set up a normal distribution? Well, like all of our other distributions, we have a set of parameters that describe the particular example that we see. They will help us to determine the mean and the standard deviation, right? Well, in the normal distribution, we actually start with those two values as the parameters. We start with a mean that represents the center of that bell curve, and a standard deviation that tells us how it is spread out around the center. So the basic structure is the same, but the scale may look a little different, and it's again dependent upon where it's located, which is the mean, and how it's spread out, which comes from sigma. If you're representing an actual population using normal distribution, this mu should represent the population mean, and this sigma should represent the population standard deviation. Obviously, we don't always have access to those two pieces of information, and when we don't, we can try to approximate them and use a stand-in for those two things. Sometimes, if our information is a little questionable, there's some drawbacks to that, and that's where the t-distribution comes in. It allows us to handle some uncertainty about the parameters that we're using. Again, we'll see that later in the course. I'll just try to highlight where that's going. For now, let's take it as a given that we understand mu and sigma and that our estimates are pretty accurate. We'll take that as given. So just a quick example. If I have a normal distribution with parameters 8 and 1.5, this is how I would write that. And what it means is I'm looking at a population whose mean is 8, whose standard deviation is 1.5, that is unimodal and symmetric in structure. And so let me just briefly sketch that out on paper so you can see what that looks like. If I were to draw in a bell curve, and I want this to represent 8 and 1.5, what I will typically do is I will draw in my midpoint, which should be my mean. So in this case, that's the first parameter. That's an 8. Then I will try to draw in successive standard deviations away from that. Okay. I'm not a great artist, you just have to live with that. One standard deviation above the mean would be 8 plus 1.5. This would be a 9.5. Okay. Two standard deviations above the mean would be another 1.5 above that. So it would be an 11. And then 3 standard deviations would be 12.5. Well, draw in my lower limit here so we can see that. One standard deviation below would be 8 minus 1.5, so that's a 6.5. Another standard deviation below that would be 5, and then one below that would be a 3.5. So this gives me a structure for where the most likely values are, right? You can look at the PDF and see, well, it's bigger here near the middle, so I expect more values to occur close to the mean. It's very, very small, far away from the mean, on either side. So most of my values will be close to the mean, and very few of my values will be far away on either side. We can quantify the likelihood of each of those things by looking at areas. So the types of questions we might ask are, what's the probability that I find a value that is between 6.5 and 9.5? Right? That'd be between 1 standard deviation below and 1 standard deviation above. Anyone know what that will end up being? Probably fine if you don't, I'm just curious if no one remembers.
Like you are?
Looks like it might be close to that. So that would represent the difference between these values. Actually, that'd be 3 here. But it's not quite right because the quartiles aren't the same. These aren't quartiles, actually. I'll show you later how to calculate the quartiles using the normal distribution. Okay, well, hold that thought, and we'll think about how to do this in just a moment. But it relates to something we've already seen. I could also ask questions for, what is the probability I see a value greater than 10? Well, the 10 would be right about here, and what I'd be looking at is what's the area to the right of that. That would be the numbers greater than or equal to 10. Okay. This question, between 6.5 and 9.5, that'd be between these two bounds. I would be shading everything in between those and asking what area does that represent. I'm not going to shade it here because I'm going to leave it unshaded for the moment, but when we do specific questions, I strongly encourage you to draw the picture, label these key points, the mean, and then a few standard deviations on either side, and then shade whatever area you're looking at. It will help you keep straight in your head how you're calculating it, because in some cases you may have to subtract from one. In some other cases you may need to subtract from 2 different probabilities to get the probability you're interested in. Okay? All right. So let's jump back to the slides for a moment. There's another special case of the normal distribution that we need to keep in mind. It's one whose mean is 0 and standard deviation is 1, which is the standardized normal curve. right? We've standardized it by that z-score process.
Are you gonna go eat the pizza?
We've moved the mean so it's 0, and shift or scaled the standard deviation so that it's now 1. That is the distribution we will use when we compare z-scores to compute probabilities. That's why it's called the standard normal distribution, because it comes from the standardization process with the normal distribution applied.
What would she think if I pick her up?
All right. Now, what does that look like? Well, here's the normal curve drawn in. So I've drawn in the probability density function for you. I didn't label the center here, but the center, if this is this distribution, the center should be 0. If it's a different one with a different set of parameters, the center will be mu, whatever that first entry is. The second entry tells me the standard deviation, and that tells me how far away from the center I have to go to collect a certain percentage of the values. Now the formula for that probability density function, you do not have to know this. I'm just showing it to you so you can see that yes, there's still formulas applied, but calculators save us a ton of time on this. Okay? We can still calculate probabilities by finding the area under this function, but the function itself is, again, pretty complicated. So the probability density function is a scaled version of an exponential. It's 1 over the square root of 2 pi times e to the negative x squared over 2. This is actually the one that is the standard normal curve. For a different one, I have to replace x with x minus mu, and the 2 here with a 2 over sigma squared. Okay. Don't worry about that, but that gives us a way then to draw the PDF for any normal distribution. Well, the cumulative distribution is what happens when I add up the area under the curve. And as I said, in calculus, we can add area under a curve using what's called an integral. And this is the integral from everywhere from negative infinity to x of that function. So this is going to compute the area under the curve up to that particular test point. Okay? You don't need to know how to do that, and in fact, even if you've taken calculus and know how to do integrals, this particular function is not symbolically integrable. Right? I can approximate it. I have lots of techniques for approximating integrals. Calculators can do it to any desired degree of accuracy. So that's the way to go. Let the calculator do the hard work. A table of values, if you're using a normal distribution table, has done this at set points that are 1/100th of a decimal place away. So 2.01, 2.02, 2.03, you'll find probabilities related to each individual value. Again, that can be done. You can calculate probabilities using that, but it's both more difficult and less accurate than computing this integral to the desired accuracy. So use the calculator when you can. So as an example for what this will look like, if I'm using the standard normal curve and I want to find the probability of the z-score less than 1, well, that means everything to the left of 0, which by symmetry should be 50%, and also everything between 0 and 1. So you can see where I shaded this. Everything to the left of my midpoint is shaded, and there's also a full standard deviation to the right of my midpoint that isn't shaded. And the area underneath the whole curve is exactly 1. The area underneath the shaded part is 0.84134. And so that is the approximate probability that I'll find a z-score 1 or less. Questions about that? So in this whole process, I don't care if you remember this formula, and I certainly don't care if you remember this formula. What I want you to know is that those formulas exist, and more importantly, when you draw in the normal curve and shade the boundary point, shade from the boundary point, you can tell which area you're looking at, and the calculator will find the exact value for that area. Okay. We will do plenty of practice problems with this over the course of the next few weeks. So what do I need to know is in place to use a normal distribution to represent my data? Well, essentially, I just want to make sure that it looks like a bell-shaped curve might fit the distribution. So when I want to work with the y-bar and the s to compute z-scores and use the normal distribution to test for probabilities, all I need to look for is, does the data I have the shape I would expect? Is it nearly normal in the sense that it is unimodal and symmetric? If it's unimodal, it has one peak. Symmetric means each side looks like the mirror image of the other, and that forces the peak to be in the middle. Since there's only one, it can't be on either end, or it'd be on both ends. So it has to be in the middle, symmetric on both sides. That naturally falls into somewhat of a bell-shaped distribution. How do I visually check that this condition is satisfied? Well, if I'm collecting individual data points, one thing I can do is I can draw a histogram. And I can say, does that histogram look like it follows a normal curve? If so, then I probably can use a normal distribution to represent that situation. Now, there are better techniques that give you a much clearer picture of whether that's appropriate or not. And one example of that is the normal probability plot. I'll show you that here. I don't expect you to use that in this course. But if you take any further statistics, or if you use this process in your job later on, you will find that a normal probability plot is a central part of deciding whether to use the normal distribution or not. All right. Key takeaway from this slide. If I want to know whether to use the normal distribution or not, I simply need to look at the shape of the distribution. Is it unimodal and symmetric? And if so, then at least in this class, I'm good for using the normal distribution. So here's what a normal probability plot looks like. I have two different sets of data. If you look at the histograms that are drawn on the side, this histogram looks unimodal and roughly symmetric. So the histogram, I would say, passes the near the normal condition. And if you look at the the normal probability plot, it's comparing the z-score I would expect if it is a normal distribution with the z-score I observe for each value. And when I do that, if the distribution is normal, then that should create a straight line. And I've said this before, it's easier for us to, it may have been a different class actually, come to think of it, it's easier for us to eyeball a linear relationship than it is any other relationship. Right? It's harder to decide if the values fall along a specific curve visually than it is to decide if they follow a straight line. And so what this does for us is it converts it to a straight line test, which is much easier to do by visualization. So looking at this one, we can see it looks pretty close to a straight line. There's a couple stragglers over here, and maybe one or two over here. But by and large, this is a pretty linear relationship. If I were trying to model this with a function, I would definitely use a line. There's nothing else that stands out to me as more appropriate there. This other distribution, on the other hand, we can tell from the histogram that it's skewed to the right. Right? There's a longer tail on the right-hand side. So it's not symmetric. It is unimodal, which is great, but it's not symmetric. And that lack of symmetry plays out in the normal probability plot, in that those z-scores no longer follow a straight line path. They instead follow some other path. Right? There is a trend here, so there's some kind of a relationship that I can probably model, but that's not the appropriate one to use. Questions about that? I won't be asking you to produce normal probability plots. I simply want you to know what they are and know how they are used. In order to produce those, you typically need software that we are not using in this course. There are plenty of software packages that cost money, which I didn't want to use, and there's also a free one called R, which the University of Maine does allow you to install, but requires a little bit of programming knowledge to be able to use. And again, I didn't want to teach you programming and statistics, so we're not doing that in this class. But be aware that it is out there and it is free. It's actually pretty easy to use once you know how to do it. But there's that initial learning curve that can take some time. Okay. All right. Well, this was a rule that we saw in, I forget which module, module 3 perhaps? We talked about probability. The 68, 95, 99.7 rule. Remember that? And what we said was, if you have a bell-shaped set of data, which now you should think of as a normally distributed set of data, then you'll find 68% of those values fall within one standard deviation of the mean. That is, between one below and one above. And 95% fall between two below and 2 above. And almost all of the values, 99.7% of them, fall between 3 below and 3 above. That means more than 3 standard deviations above is about 0.15%. In other words, the probability of a value more than 3 standard deviations above the mean is about 0.0015. That's very unlikely. Similarly, by symmetry, the probability of a value more than 3 standard deviations below the mean is 0.0015. The symmetry allows us to take values to the right versus values to the left of symmetric points as having the same probability. They'll have the same area on either side. Okay. So now we can think about this 68% idea as the area between -1 standard deviation and +1 standard deviation compared to the mean. This area is actually 0.68 approximately. Okay. So let's go back to the example that I was looking at a moment ago on the document cam. When we drew in the normal distribution with 8 and 1.5, I asked about finding these kinds of probabilities. Okay. The probability of the next value between 6.5 and 9.5, well, that's 1 standard deviation below and 1 standard deviation above. So by the empirical rule, if this is a normal distribution, that should be approximately 68%, 0.68. We'll actually compute this on the calculator in just a moment, just to see. And I don't know what 10 would be, right? But I could probably estimate it. I have 34% to the right here, since this is symmetric. The 68% is split into 2 pieces, 34% on each side. 50% to the left of 8, 34% from 8 to 9.5. That means 84% are 1 standard deviation above or below it. And 10 is just beyond that. So I'm going to have roughly maybe 10%. This is just my eyeballed estimate. I think I'm going to get an area of about 10% as I go from 10 and to the right of it. Alright, let's see what the actual value is. I didn't do this in advance, so I'll be just as surprised as you are when we see it. Let's jump to Bogdan's calculator. As I mentioned, he has calculators for everything we need. Since we're now in continuous distributions, let's look down here. Here's the normal distribution calculator. So when I click on it, the default is the standard normal distribution. If that's what I'm starting with, that's what I should use here. If you compute z-scores, simply use this default and you'll get the correct probabilities. But one of the advantages of using a calculator is you don't necessarily have to convert to z-scores first. If you use the table of values, you have to convert to z-scores, then you look at the table for area corresponding to those z-scores. Whereas here, we can do it without that. I can look at that 8 as my mean. Notice it moves to the center. And I think I said 1.5 as the standard deviation. So here's that graph. All right. And I want to find the probability that I'm greater than 10. So there's 10. I'm shaping the area to the right of it. That's what the greater than part does. It computed the exact area. I estimated about 10%, and the correct value is 9.121%. Well, what's the probability that I'm less than 6? Same number, because it's the same point on the other side by symmetry, right? If I move from 10, which is 2 above the mean, to 6, which is 2 below the mean, and I change from to the right of it to the left of it, that's a perfectly symmetric situation. So the area to the right of 10 and the area to the left of 6 should be the same. You can take advantage of that in some cases, but there's no extra cost with the calculator. It's easy to just recalculate things every time if you need to. Now, how would I find the area, say, between 6 and 10? What would I do here? Let's sketch it out on paper so we can see what we're doing, and then let's use the calculator then to compute that result. Okay. So I'm going to scroll in here, my normal distribution. I'm only going to label the midpoint and then 2 points I'm trying to calculate the area between. Okay. I want to calculate the area between 6 and 10. Well, here's what I can do. If I'm trying to compute this area right here, all that my calculator will do is tell me the area to the left of 10, or to the left of 6, or to the right of 6, or to the right of 10. One thing I can do is I can take the area to the left of 10, which is this entire area, right? And then I can subtract from that the area to the left of 6. What's left over is the area that I want. So what I'm using is I'm actually using this idea. The probability that x is less than 6 plus the probability that x is between 6 and 10 is the probability that x is less than 10. Alright, if I add up the area here and the area here, I get the total area up to this point. That's what this says. So if this is the value I want, I can just move this to the other side. The probability that x is less than 10 minus the probability that x is less than 6. Because everything left over in that range is a number between 6 and 10. So I can use the calculator to find those two values. The probability that x is less than 10 on my calculator is 0.90879. The probability that x is less than 6, less than 50%, is 0.09121. That's the same number we saw a moment ago. And when I subtract these two things, I'm going to get roughly 81%, maybe 82%. Right? Do that carefully to make sure I get the right answer. 0.90879 minus 0.09121. 81758. Okay. And obviously there are more decimal places than this, but this is the number of decimal places that Bogner's calculator gives me. If you use a TI-83 or TI-84, you can get more decimal places than this. It should not be necessary in this class. I think almost all of these ask for 4 decimal places, and that should be correct if you use Bogner's calculator. Questions about that idea? This idea of subtracting the area to the left of different endpoints, giving you the area between those endpoints, is very important to calculating probabilities for the normal distribution. You have to be able to sketch out the picture to figure out what your shaded area is and where it lives with respect to the areas you can compute. All right. So let's slide back into the slides now. Let's do this for a particular normal model for birth weights. If the average birth weight is 7.6 pounds and the standard deviation is 1.3 pounds, and we think we can use a normal distribution to model this, then we can sketch this particular model and then compute areas to find the probability of a birth weight falling in a certain range. Okay. All right. So I'm going to start by sketching that. That's where I recommend you always start. Okay. I'm a terrible artist, but we can live with it. All I need is a basic shape. I want 7.6 as my mean. And I'll just use solid lines here. 1 standard deviation away is 1.3 above. That's terrible. Okay. 1.3 above that is 8.9. 1.3 above that is 10.2. And lastly, 1.3 above that, for whatever reason, my right-hand side seems to always go up, is 11.5. Gives me a basic picture. So on the other side, I subtract 1.3 each time. This would be a 6.3. Subtracting 1.3, this would be a 5, or 5.0, I just don't have space. And 1.3 below that would be a 3.7. And so what this tells me is about 68% of birth weights should be between 6.3 and 8.9. About 95% should be between 5 pounds and 10.2 pounds. And 99.7% should be between 3.7 pounds and 11.5 pounds. It should be very rare to find a birth weight above this and a birth weight below this. All right. Backtracking from that, in what range will I find 95% of all babies' birth weights? Which two values?
Between 6.3 and 8.9.
So how many standard deviations above and below is that?
1.
1. And the empirical rule tells us that 1 standard deviation gives us the 68%. Remember, it says 68, 95, 99.7.
Mm-hmm.
So I want to be 2 standard deviations away.
Five, 10.2.
5 pounds and 10.2 pounds. According to this model, that's where 95% of birth weights should fall. Where is the 84th percentile?
Somewhere between the 68th and the 95th.
Okay. So I see what you're thinking there. And you're right, 84 is between 68 and 95, so it's definitely going to be somewhere in this range, right? Here's the best way to think about it. Where's the 50th percentile?
The mean, 7.6.
Right, because of the symmetry, the area to the left of it and the area to the right of it are the same, so that's the median and the mean. It's the 50th percentile. So I have 50% of the area here, I have 68% of the area equally spread on both sides of it here. Half of 68 is 34. And if I take 50 and add 34, I get 84. So turns out the 84th percentile is actually 8.9 pounds. And if you can reason through that, that's excellent. If you can't, that's okay. There is a way to use the calculator to find it. So let's verify this in just a moment. In fact, let's just do that now. I'll jump back over to Bognar's calculator again. And we will check with 7.6 as my average birth weight and 1.3 as my standard deviation. I want to find the 84th percentile. And so what that means is I want the probability that my variable is less than this bound to be 84%. So what I'm going to do is type in as 0.84. I want the area to the left to be 84%, and it will tell me the boundary that makes that work. The 84th percentile is 8.8928, which 8.9 is what that rounds to. The difference here is the fact that the 68, 95, 99.7, it's not exactly that. It's actually like 68 and a change, and a little less than 95, and a little more than 99.7. I mean, it's one of those things where you have to kind of be precise, and the calculator will give us the exact value. But to one decimal place, as we have here, it's the same number, 8.9 pounds. All right, questions about that? So Bogner's calculator gives us a way to go from a boundary point to an area to the left or to an area to the right. It also lets us move in the opposite direction. If I have an area to the left and an area to the right, it will tell me what boundary point will cut that area off. All right, if I want to find, for instance, the median, that means exactly 50% is to the left of it, and it's not surprising that the median is the same as the mean because it's symmetric. But if I wanted to find the first quartile, that's a little harder. The first quartile is the number that is in front of 25% of all values. So the 25% will be the area to the left. If I simply type in 25%, there's my first quartile. So 25% of all birth weights will be at 6.72 pounds or below. Okay. And that comes directly from this particular formula. Similarly, I can find the 75th percentile, or the upper quartile, this way. That's the 75th percentile. It's the birth weight that is above 75% of all birth weights and below the other 25%. That is 8.48 pounds based on this calculation. I can also do it as it's below 25%. Right? If I just typed in the 25 and had it calculate, type it in, I guess. Why it doesn't want to do that.
You're greater than.
There we go. And I was trying to do that on purpose to show that you can do the greater than. It's the values that are greater than the upper quartile represent 25% of them. Right? 25% of values are above that 75th percentile. Equivalently, below the 75th percentile, you'll find 75% of the values. Depending upon which way you frame that, you can think about the area you'd expect on either side, and the calculator will find the boundary point in both directions. Okay. Okay. You know what? Let's keep going. What percentage of babies will have a birth weight over 9 pounds? Using that same model. So if I were to sketch it out on paper, I'll use the same thing here. What percent have a birth weight above 9 pounds? So when I'm solving a question like this, what I want to do is I want to draw in the boundary point I'm talking about. So 9 is just past this 8.9. And then shade the part that I am considering. So above 9 pounds or over 9 pounds would be to the right of it. So this is the area I will shade. Okay. Now, I always recommend thinking about roughly what you expect so that when you do the computation, you can compare what you get from the computer or from the calculator with what you'd expect, and if they're close, you can feel pretty assured that you did the right work. If they're not close, you made a mistake, and you can figure out where that mistake was by consulting your picture, your written work, or your calculator. It's usually one of those three things. So what would I expect this area to be?
30%?
Not quite, actually, because this 8.9 is the 84th percentile. Right? So 16% of the values are above it. And I'm actually looking at a number just a little bit past the 8.9, so it should be a little less than the 16% above this. So I expect, I'm writing this down, you don't have to write this down, but I'm making this note to myself, I expect less than 16% or less than 0.16 as a probability. How much less depends on how far it is and where in the curve that happens, but at least ballparking it, I know it's going to be less than a sixth. Okay. All right, let's check the calculator. That one, and I want to find over, yes, I will in a moment, 9. So like the probability is 14%, which lines up with the little bit less than the 16% that I expected. Okay, so my probability that my birth weight is bigger than 9 is approximately 0.14076. Okay. Now that's what I get from the calculator. Let me show you how you would do this using the table of values. Okay. So for table of values, I want to find the probability that x is greater than 9. The table of values will give me an area to the left. It won't give me an area to the right. What I can do is I can use the fact that the area to the right of 9 is 1, the whole area, minus the area to the left of 9. I'm going to write that down in symbols. The probability that x is greater than 9 is 1 minus the probability that x is less than, or less than or equal to 9, technically. But again, I don't need to worry about those equal signs. If I include the 9 or don't include the 9, it makes no difference because the probability of 9 is 0. That one value has no impact. All right. So I can't compute this directly, but I can compute this, and I can take 1 minus the answer to C. Now I should get about 14%. Let's see what the table of values gives me. So I'm going to use the table in my slides, which I will try to zoom in on. Bear with me for a second. All right, so hopefully you can see this. I need to compute a z-score for 9 pounds. Okay? Once I have a z-score for 9 pounds, let's say that my z-score is 1.22. Then I look here at z equals 1.2, and I look where the second decimal place is 2, so 1.22 is right here. The area to the left of that point would be 0.8888. And so the probability I would be looking for is 1 minus that number. That would be 0.1112. If I did that in my head correctly. No, I don't think I did, but that doesn't matter. Let's do it for this value. Let's actually compute the z-score and then verify that we get the 14% that we expect. So how do I find my z-score? Alright, so when I do a z-score, I always write observed minus expected over standard deviation. You can do whatever you want with that, but in my experience, if you write this down first, you plug the right pieces in the right place, and it keeps in your head the idea that this z-score adapts to different situations. Here, since I'm doing it with a normal model, the observed value is the boundary point I'm looking at, the 9 here. I'm trying to calculate this thing right here. So the observed value is 9. If I were to make a prediction for an expected value, I would expect the number right in the middle. Right? If I'm randomly guessing what the birth weight of an arbitrarily chosen baby is, it's probably going to be right at the median, or right at the mean. And that's the 8.9. Okay? No, not 8.9. 7.6, I'm sorry. Is that right? Yes, 7.6. And then my standard deviation was the 1.3 that I was told. And so I can now compute from this the z-score I expect. And it should be bigger than 1, come to think of it, because 8.9 is 1 standard deviation away. 9 is further away than that. So it should be a little bit bigger than 1. Let's see exactly how big. 9 minus 7.6 is 1.4. And 1.4 over 1.3, I'll do that quickly on the calculator. The value I get is 1.076923, etc. 1.0769 is what I'll write down. When I use a table of values, I have to round to 2 decimal places. So that goes to 1.08. Okay. Obviously, this is rounding. That will produce a little bit of error. Okay. That's okay. I should still get a number pretty close to the right value here. We'll see exactly how close. But this is where I want to warn you. The questions on the homework and on the exams are designed to use the calculator. So they will expect no rounding error in that sense. Use the calculator for those. Make sure you understand this process when you use the table. Okay. I want to look up in the table to find the probability. The probability x is less than 9 is equal to the probability that my z-score is less than 1.08. And that's the value I can read off from the table. Once I have that, the probability that x is greater than 9 is going to be 1 minus whatever value I get here. Okay? So let's look that up in the table. Go back to this. Zoom in. All right. So I want to look for 1.08. So I follow my z-scores down to the 1.0 row, and I go until I hit the 1.08 column. That's right here. So the area to the left of 1.08 on the standard normal curve is 0.8599. 8599. And if I take 1 minus that, which is the formula I want to use here, 1 minus that value, it should give me a pretty good approximation for the probability that x is at least 9. And that's pretty close to the number we found. All right, 0.1401. It's not the same, especially in the 4th decimal place, but it was roughly 14%. I think it was 14.06% or something like that. And by this calculation, I found 14.01%. That's the cost of the rounding error. It makes some of my later decimal places incorrect, but ballparking it, it's correct. It gives me the right basic percentage. All right, are there questions about how to use the table of values that way? So I included the table of values here in the slides. You can use that if you want to try some this way. There are plenty of examples of tables of values on the web. I think your textbook even links to one that's from the federal government, National Institute of Standards, I think it is. But it's useful in a lot of places, so having a table of values and knowing how to use it is not a bad thing. But of course, if you have access to a calculator, it will be both easier and more accurate. So that's what we'll do in this class.